All right. Yeah, sure. Sure. Just please let me know if you can see my screen. Okay, the presentation too. Uh, okay, then I'll start. All right, so hi everyone, my name is Mahsa, and it's my pleasure to be back at ECC2 this year. But although I'm very sad that I couldn't make it again in person, hopefully next year there will be like no virtual talk at ECC, and then we will all be able to meet in person. All right, so my talk, as you can see here in the title, is going to be about fully on-chain order books. But before I start, very briefly about myself, I'm doing PhD at Concordia University in Montreal, Canada, and my research is mainly on decentralized finance and blockchain applications. And also, very recently, I have joined the Off-Chain Labs to be working on Arbitrum as a part-time software engineer. All right, so let's dive in. And to begin with, let's assume that you have a very great idea of some sort of financial application for blockchains. And the good news for you is that there's really no barrier for you to do so. You can just go ahead, you can write it up in some form of code, we call it smart contract, and then you push it to the Ethereum blockchain, and Ethereum will give you some sort of security guarantee that the code that you wrote will be executed exactly the way that you wrote it. And that's actually the message that I'm trying to communicate here is there's really no barrier to entry for any kind of decentralized financial application nowadays on a blockchain. And that's the reason why we're seeing a huge growth in DeFi space now. And at this moment that I'm talking to you, there's actually the total value of 56 billion US dollars worth of tokens or other Ethereum assets that are locked in decentralized finance. And that number is huge. And I guess it's scary too, because Ethereum is really is a very hostile environment because it's totally unregulated. So on the other side of the story, we have governments and financial regulators who really want to provide consumer protections for traders or other users of these kind of DeFi services, but they are really worried and they're concerned because they almost have no ability to do so when it comes to those services that operate fully on chain. And among those regulators was Quebec's regulator, Autorité des marchés financiers, or MF, that they actually approached us. It was a year ago that they came to us and they were really worried and concerned about on-chain order-driven exchanges. And they really wanted to know if such a service is feasible to be operating on Ethereum today or anytime soon. So to answer the MF question, what we had to do as researchers was we actually went out to see if there's any order-driven exchange that operates fully on chain that we could find so that we start running some performance tests or do some investigations. But unfortunately, all we found was a bunch of white papers that were just talking about what fully on-chain exchange is or what would be the benefits. So to avoid any sort of speculations, what we did was we actually rolled up our sleeves and we started building and implementing an order-driven exchange on Ethereum so that we could see what would be the performance benchmark. So all the results of our research and investigations are provided in this research paper that is publicly available online. And in the rest of my talk, I'm going to provide some high-level details and interesting discussions of the paper for you. So basically, more specifically, actually, what we're going to learn in this presentation, first off, is that we want to know if secure trading, such as resistant to front running, is really feasible as a fully on-chain service on a public blockchain, specifically Ethereum today. And if it is possible and feasible, what would be the performance benchmark? And we're also very curious to see what would be the effect of a novel Ethereum scaling solution, for example, rollups, on the performance of such a system. Right, so for designing and implementing an order-driven exchange, we had to first decide about the data structure. So we know that most of the exchanges use something like called an order book, which is an electronic data structure for storing the incoming orders, and keeping them sorted. So what we thought was, so order book is a ledger, and blockchain technologies give us distributed ledger. So what we thought was, there's this data structure that it works like a table and it gets updated. So why don't we just throw it in a form of some smart contract on Ethereum? That sounds really cool, right? So that was the potential design that we had in mind, but it actually it turned out to be really infeasible because there were quite a few challenges that we faced, and I'm going to explain them to you now. First off, most of the exchanges, they operate on a price time priority manner, meaning that orders in the order book, they are sorted and they're executed based on their price. And if there are two orders that they arrive to the order book with the exact same price, the one that has arrived to the order book first, it gets executed first. But that's the problem that we have on a blockchain. There is no centralized time server on a blockchain. There's no way that we can establish the time priority. And if Alice actually is more well connected to the network than Bob is, then her order is executed before Bob, even though she sends it after. So we actually have no way to say who was first on a blockchain. Another problem that we have is that blockchains are typically slow in compared to markets. And stock market, they actually move very, very fast. And the example is high frequency trading, where there are active dealers or computers that they are trading based on nanosecond levels. And this is really a problem because blockchains are slow and it takes intervals for transactions to be confirmed and included in a block. And the other problem that we have on a blockchain is that blockchain is an open public network. So everything is public. So every transactions that is broadcast to the network, it can be seen by everyone before it can be included in a block. So what we have here is nodes. They can censor transactions. So they can see an order and they can just, they feel like this is really competitive for them, and then they can just drop the orders and simply not propagate it enough to the network. And miners are even in a more powerful positions because A, they are the ones who decide what to put inside a block, and B, they're the last ones to see the transaction inside a block before it gets mined. And basically what they can do is they can just wait till the very last moment. After seeing all the transactions inside a block, they can just insert their owns and just benefit from that. And the other problem is front running that we have with a miner. They can actually see all the transactions inside a block and they can just beat you with a better price. All right, so because of these challenges that I just explained to you, it turned out that we cannot really dump an order book on a public blockchain. So what we had to do was we had actually two options. Either we close the network, and instead of Ethereum, we would just use something like Hyperledger or L3 Corda, where not everybody can be a miner. So we would actually eliminate the problem of censorship and front running. And also there would be some centralized time server that enforced the time priority. The other option that we had ahead of us was to stay on a public blockchain and still get all those benefits that we could get from Ethereum, but we use an alternative data structure to the order book. So we choose the second one. We actually wanted to stay on Ethereum because first off, it's a more hostile environment. So if we can get something to work on Ethereum, it can only work better on other private network. And so what we chose was something called a call market. So unlike an order book, the way call market works is more like an auction. So the auction sort of opens and bids and asks are submitted, but they're not executed immediately. They just sit inside that data structure inside a call market until the auction is closed, and then the orders that are overlapping against each other, they trade against each other. So how would a call market solve those problems that I just explained? First off, here in a call market, we're batching the transactions. So there's no time priority anymore. So either you get inside the auction when the auction is open, or you not. So there's no time priority here. And about blockchain being slow, call markets are slow too. We actually accumulating all the orders in a 7-minute period or so. So that solves the problem too. For censorship of transactions, in our design, we urge the nodes to broadcast as much as they can so that at least one honest node in a network would see the transaction and would include that inside her block. And for miners front running, we use the MEV and turn it around for good, and we give the price improvement to the miners in our design and implementation, and that would disincentivize miners to front run well-priced order. All right, so now that we know we want to implement a call market, we have to choose the ideal data structure for storing the orders that arrive to the market. And in a call market, closing the market and processing all the orders is done in a batch, in one single transaction. And having the limit, the block gas limit in Ethereum, that would be the really, like, it would be the bottleneck for us because it's the most expensive step for us. So we had to choose an ideal data structure to handle this issue. And what we chose was a priority queue, which is a data structure in which each order, each element has a specific priority. Here would be the price. So we use two priority queues, one to store the bits when the highest price is the highest priority, and one to store the incoming ask where the lowest price is the highest priority. So I won't go really through the details of the performance test, but we implemented 5 different priority queues. We ran a lot of performance tests on different, like enqueuing or dequeuing different elements inside each PQ to find out which one has a better performance, because again, performance was the main bottleneck for us. So it turned out that the linked list with mapping is the best priority queue for our implementation. We implemented a call market. Our system is called Lissi. It's written in 324 solidity lines. And we kept it as a simple module so that it could be extended by developers the way they want. And yeah, so how it works, it basically works like an auction. So the market opens, traders would submit their bids and asks, the market closes, and then in one single transactions, all the orders would be traded against each other. So there are 8 main operations in Lissi. We have deposit token and Ether. So traders would have to deposit their ERC20 tokens and Ethers they want to trade inside a smart contract. Then we have open market and close to open and close the market. Then we have submit bids and ask function for traders to go ahead and submit their orders. And after the market is closed and the orders are settled, the traders, they can come along and they claim their tokens and Ethers, calling the claim tokens and claim Ethers functions. All right, so now that we have the design, we revisit this question again. How many orders we can process in one single Ethereum transaction when closing the call market on Ethereum today? So we ran a lot of performance tests again for each different priority queue that we implemented. And the first column shows the highest number of trades we could handle in each case. And you have to pay attention that this is for the block gas limit of around $12 million when I ran these performance tests. And the next column is those gas costs for those numbers. And because we knew that Ethereum is going to be improved and we would be able to handle more transactions inside each block, we just ran the test for 100 trades to see how much gas it would cost. And the last column shows the gas price for submitting the orders for each priority queues. So as you just saw, the bottom line is we can only handle 100 trades on every single closing on Ethereum, meaning layer 1 today. And that would really would position Lissi or call markets for a small set of markets, for low liquidity markets or low number of traders. But there are Ethereum scaling solutions that they actually improve scalability of Ethereum a lot. So using we actually use Arbitrum rollup. So we implemented a variant of our system on Arbitrum testnet, RINC-B, and we actually found that it reduces the cost for executing the trades by around 99.9%. And pay attention that using such a scaling solution, we could actually do an infinite number of trades per closing. And this is really fascinating. So if you want to know what Arbitrum is, it came out as a research paper in 2018 by a group of colleagues at Princeton University. You can just go ahead and read the paper. And yeah, that's it. So we have a lot more discussion points inside the paper that I couldn't cover in this talk because of the time. We have front-running evaluation of different kind of order books, call markets, and that is really interesting if you want to go ahead and take a look. We have discussions around who would close or open the market, or how we calculate or not calculate the market clearing price. And we have some gas refunds discussion, and we have talked about their limitations as well. So that would include my talk. Thank you so much for attending. If you need to contact me, the first one is my Twitter handle. The paper is again publicly available on the archive. Feel free to go ahead and read it. And yeah, don't hesitate to reach out if you have any questions or suggestions. Thanks. Yeah, sure. Yeah. So for your first question, we actually thought about this too. And in the discussion point, we had some alternative design decisions for closing the market. And we actually have such a design too, that closed market would happen in different stages. So in the first closed market, only n number of orders will be processed, and the second closed market, like another set of transaction will be, clear too. Yeah, we just wanted to find the benchmark of like what would be the benchmark, the baseline of how many orders we can process. But of course, there are more kind of like design alternatives to this too. Yeah. And for market clearing price, in our design, like intentionally, we don't calculate any market clearing price because we thought miners could really manipulate this like on Ethereum. So we don't do that. And if that's needed, we can just use some third-party services to to calculate the market clearing price. Mhm. So we intend to open the market inside a block, and at the end of the block, we close the market. But of course, that would really need us to monopolize all the block, right? Like, yeah. And the market that we design is a short-lived market. So the orders, like, it's only like 5 minute period. So we open the market for 5 minutes, and then after that, the market is closed and orders are matched. Right, right. Of course, yeah. Yeah, that's actually that's a very good point, and that's right. I don't know, but yeah, we could look at it as a trade-off between using an on-chain exchange and a centralized exchange, maybe. Yeah, but yeah, sure, of course. Yeah, I'd be happy to, because this is a very interesting point. That's also a potential solution, right? Yeah. But yeah, I'm happy to take this offline with you because it was a really interesting point. Yeah, all right, thanks. Yeah, because like on decentralized exchanges, so-called decentralized exchanges, there's one some of functionalities are being done on chain for like loading balances, but still matching orders and other settlements are being done off chain. So if anything happens, there would be some entities that regulators they can go after and find out what happens. But when everything is done fully on chain, there's if anything happens like stole of funds or like any other issue, there's no way for regulators to go ahead and like find out what's happening because there's no actual person like behind these things. It's fully on chain, it's fully anonymous. Yeah. Oh yeah, so I'm not I'm not actually comparing myself to AMM. I'm just talking about an order-driven markets, like us with an order-driven centralized exchange. Yeah, sure. All right, thanks. Good luck. You too. Take care. Bye.
Hi there. Good, and you?